Good morning, gang. Let's see what's going on here. Okay, so today, a few things. Sorry. I haven't finished marking y'all's exams just yet, so I'm going to ask you to be a little bit patient with me, but I'll have those grades in today. And I do want to start by talking a little bit about that. So, grades will be in before the end of the day today. And from what I've seen, things are pretty much okay, but I'm going to run some statistics. This is the first time I've done an exam in this format, where the questions are there in Canvas, you have to type something and then submit. And I want to make sure that I'm being fair. When I finished looking at all of my Calc 1 stuff, I noticed that a lot of my Calc 1 students didn't have time to finish the test because they seem to be struggling a bit with the format or something. And so I'm considering allowing something like a rewrite for them. So after I look at the statistics, I may consider a curve or possible rewrites. Because if you are unable to get to a question, then I don't like the idea of just giving you a 0 for that. I would rather see what you're capable of. So I'll ask you to be a little bit patient with me. The scores you're going to see going today are going to be the raw scores. Those will be the scores just graded straight according to the rubric. And then I'll look at some stats. And if I determine that a curve or rewrites or whatever are a valid thing for our group for this test, then we may end up doing that. I haven't decided exactly how I'm going to do that for my Calc 1 kids, but if I end up doing it for you guys, I'll do it the same way I do it for them. And it would probably be some sort of timed, it would be like a test, but with just 1 or 2 questions if there's like a question that nobody got to, that sort of thing. So that's what I'm looking for. I want to make sure that everything is fair. Peter asks, how is the grading going to work? So the way things are set up in the gradebook is right now I have both of the assignments for exam 1 worth 50 points. If you look in the syllabus, exam 1 is worth 100 points, right? Each of the midterms is worth 100 points. So I'm going to, both of those scores in the gradebook will be the same, and they will total to a possible 100 points. So I will write little comments explaining exactly how the grade breakdown works. But basically, you'll see, if you earned 50% on the exam, then you'll have a 25 and a 25. And that seemed to be the easiest way for me to kind of jerry-rig the gradebook so that it will work and still sit with our rules in the syllabus. They should both be worth 50 points in there for a total of 100. Take a quick look. 50 points here, 50 points here, yeah. So the exam 1 questions and the exam 1 submit your scanned work for exam 1 here. When you see the scores for these 2 things entered in the gradebook, they will both be the same. And they will, the total possible points is 100, 50 in each element. So to find your total score on exam 1, you'll add the score from both of these assignments in the gradebook. And when I put in the scores, I'll put a little comment there that has your total score. So 2 questions. Caesar asks, can we work some homework problems? Yeah, sure. And then Peter asks, if you made a mistake and then that mistake like propagated, but your process was correct, will you still get some points? Yeah, of course. My goal, the point of having you submit your work is that I can give you as much partial credit as I can possibly justify. Let's put it that way. So I'll be on your side as I mark these things. I assure you. I want to give you credit for all of the good stuff you do and only take points away for the mistakes you make. So if it's one little mistake and then that like number follows you for a while, I'm only going to mark off for that first time you made the mistake, and I'll be as generous as I can. Caesar would like to look at number 13 from the homework. So we'll get started with a few problems from the homework, and then we're going to talk about sequences. So 13 seems popular, 12, 17, 18, 23. We can look at some of those, probably not all of them, but some of them. So let me come here. I did just go through and clear out my extension request. So if you needed more time on this and submitted an extension request, that is now in. And you should be able to get back in. 13 is the only one that multiple people requested. 6 and 13. 12, 17, 18, 23, 12, 2. All right, so 12 and 13 both seem popular. Let's look at 12. We want to know whether this integral converges or diverges. And if it's convergent, we want to find the value. Okay, so let's do this. I'll copy this guy down and then we'll switch over to the .cam. So this is homework 6, number 12. We want to evaluate the integral from -∞ to 0 of z over z to the 4 plus 81 dz. So we're going to start there. It's not that bad. I mean, it's not nice. It depends on how you choose to start. So, of course, the very first thing we need to do is rewrite this as a limit. R goes to -∞, integral R to 0, z over z to the 4 plus 81 dz. I see a relatively painless way to make this go. I'm curious what everybody else tried. It seems like a lot of us didn't enjoy it. So here's my suggestion. Let's start with this little u sub. Let x equal z squared. Then dx is 2z dz. That will be gobbled up by the z upstairs here. Also, my bounds will change. When x is equal to r, or sorry, when z is equal to r, x will be equal to r squared. And when z is equal to 0, x will also be equal to 0. After this, we'll be able to evaluate the resulting integral in terms of the inverse tangent function. Dalton asks, should you feel nervous if you need to use Desmos to visualize these graphs? Most of these graphs are a little bit challenging to picture. So yeah, I wouldn't panic if you looked at Desmos for a lot of this stuff. The graphs themselves won't help you too much when it comes to solving these problems, but for the purposes of looking at the functions and trying to make a guess, no, don't feel bad if you looked at Desmos. That's okay here. Good question, relevant question. I like that. I like that you're thinking about it. But yeah, no problems looking at Desmos for these graphs. Z over z to the 4 plus 81. I can guess a little bit what that looks like because I know what x over x squared plus 1 looks like, and this is kind of similar to that. But even I don't know off the top of my head just what that graph looks like. So my new integral is going to go from r squared to 0, z dz, that's 1/2 dx, and what's left is 1 over x squared plus 81. Right? Z to the 4 is x squared because x is z squared. And I can pop out my 1/2. He can come all the way out past the limit even because he's a constant. And my integral becomes this. And if you've remembered the arctan formula that I showed you and recommended that you prove leading up to exam 1, this is a straight up arctan integral. So a here is 9. So I've got 1/2 lim r to negative infinity. Sorry, there should be an r squared down here. Sorry. Lower limit here is r squared after that sub. And then what do I get? I'll have 1 over a, so 1/9 times the inverse tangent of x over a, x over 9. And this is all to be evaluated from r squared to 0. So the integral is a u sub into an arctan. It's not too bad. This 1/9 can come out. So I'll have 1 over 18 lim r to negative infinity. And then inside I'll have the inverse tangent, inverse tangent of 0 minus the inverse tangent of r squared over 9. Like this. So the formula that I'm using there is again the one that I recommended you prove, that the integral of 1 over x squared plus a squared is 1 over a times the inverse tangent of x over a plus c in that indefinite form. So little substitution followed by that will make everything come out nice. You could do some trig sub here, but it's overkill. You don't need to do it. Why did I take the 9 out from the bottom? So this 1/9 comes from this formula. And I'm able, because it is a constant multiple, I'm able to bring it out and multiply with the 1/2 to get 1/18. And then here I'm writing arctan of 0 because 0 over 9 is 0. You could write it as arctan 0 over 9 if you wanted to, but it's the same thing. So I get 1/18 times the limit as r goes to negative infinity. The inverse tangent of 0 over 9 is the inverse tangent of 0, which is 0, minus inverse tangent of r squared over 9. Now this is a place where we should not have to look to Desmos. If you don't know what the graph of this function looks like and you look at Desmos for that, that's okay. But if you need Desmos to find this limit, that's not okay. So let me show you how I would do this limit. My 1/18 comes along for the ride. As r goes to negative infinity, r squared goes to positive infinity. Positive infinity over 9 is the same as positive infinity. So this is 1 over 18 times the negative inverse tangent of infinity. That's the nice way to think about it. And arctan of infinity is pi over 2. So this is negative 1/18 times negative pi over 2, or negative pi over 36. Yeah, Dalton asks, how did I know to sub for z squared? Two things. I've got a z dz up here, which is the piece that I'll need for a z squared substitution. And also, yeah, looking at this denominator, I know z to the 4 is z squared squared. So I'm able to see that under that substitution, this will become something like this. So pretty much right away, I'm thinking arctan. I'm thinking this looks like a little substitution into an arctan thing. The z to the 4 is z squared squared. So I'm like, I can reduce that power if I substitute by z squared. And then I ask, do I have what I need to substitute for z squared? Yeah, I do, because I've got this z up here. So it kind of jumps out at me, right? Seeing this even power here automatically makes me want to sub for z squared because there are no odd powers anywhere downstairs. And then seeing this up here reinforces that, because that tells me, oh yeah, not only would this become nice if you sub for z squared, but the pieces you need to make the substitution go are readily available. And so Fernando asked, does that mean this integral is convergent? Yeah. Yeah, therefore, the integral converges to this value. I'm not sure I follow the question, Gustavo. Could I ask you to say that again, or to maybe rephrase it for me? So the 0 here is coming from the upper bound of 0 here. When I plug x equals 0 into this, I get inverse tangent of 0 over 9, which is the inverse tangent of 0, which is 0. So this guy doesn't have anything to do with the infinity stuff. All the infinity stuff is coming from this piece.
No, what I mean is if I take if I use tangent instead of arctangent, it is negative. It is infinity, right?
If you use the tangent instead of arctangent, where?
No, what I'm thinking is I don't quite understand why arctangent of infinity is pi over 2. That's what I mean.
Okay. Yeah, that I can help with. So remember what the inverse tangent graph looks like. And this is what I was saying. So this is one of these graphs that we really need to know. If you do find yourself leaning on Desmos for this part, then there is something there that you need to go back and study. And for this problem, it's this. So the horizontal asymptote out here is y equals pi over 2. And the horizontal asymptote down here is y equals negative pi over 2. So as the inside of arctan goes off to infinity, the outside gets closer and closer and closer to pi over 2. So the limit as x approaches infinity of arctan x is pi over 2. And an easier way to say that is that the arctan of infinity is pi over 2. Regular tangent of infinity, this does not exist because the tangent function is periodic. So regular tangent here, I don't care about, but the inverse tangent of infinity, or the limit as the inside of arctan goes to infinity, is pi over 2. The unit circle can be helpful here. It can, but really this inverse tangent graph, this is one that we really should know. This should be a close friend of ours. He's a super important function. I don't expect you to have memorized the graph of the inverse secant function or cosecant or even the inverse cosine function, but the inverse tangent function is sufficiently important that we should know this graph. So if this isn't familiar, I understand a lot of trig classes go way too light on inverse trig. Now is the time. Okay. Other questions on this fellow? So if you don't see this substitution, this is a hard problem. I agree. The trick is definitely seeing this substitution.
Excuse me, the original problem, it is c to the 4. And after you're doing the substitution, you change it by x squared plus a1.
So how did the denominator become this? Is that the question?
Yeah.
Okay. Let me come back over here to discuss that. So z to the 4 plus 81 is the same as z squared plus 81, because a to the b all to the c is the same as a to the b times c. So z to the 4 is z squared squared.
Oh, okay. Oh, okay.
If x equals z squared, then 1 over z to the 4 plus 81 is 1 over x squared plus 81. Yeah, just some sneaky algebra. So good. What else do we want to know? Yeah, Gustavo, go ahead.
No, okay, no. What you do was replace like c squared by x, and for that reason x squared plus 81.
Yep. Yeah, exactly. So this piece right here is what I'm replacing by x. Dalton asks a good question in chat, but we got to be a little careful with parentheses. So negative infinity squared, like this, that would be negative infinity. But negative infinity squared like this, that's positive infinity. So the easiest way to think about infinity, and there's actually, I can talk about this for a minute, just replace the word infinity with huge number, unimaginably huge number. If you take an unimaginably huge negative number and square it, you'll get an unimaginably huge positive number. So yeah, negative infinity all squared, that's positive infinity. There's a guy named Doron Zielberger. I won't say any more than this. At Rutgers. He follows a school of thought called ultra-finitism, meaning he does not believe in infinity. Famous mathematician, world famous, very talented. And he would just straight up tell you these things don't exist. Just when you use this symbol, think of big number. But we don't need to go there. That's getting silly. So there were some other problems that we wanted to look at. 12 and 13 were the most commonly requested. So I'll go ahead and do those, that other one, 13, before we move on to talk about sequences. So 13 is the integral from 0 to infinity of e to the negative square root y dy. We want to know whether or not this integral converges, and if it does converge, we would like to find the value. This guy also requires a little u sub, and he's kind of sneaky. But first we need to rewrite it as a limit. So always this first step of rewriting as a limit, that's what allows us to do all of the calculus we love. Remember, you can't build a Riemann sum for this, you can build a Riemann sum for this. So this first step, although it might feel kind of artificial or unnecessary, very, very much necessary. And then we look at that integrand and we say, what the fuck, right? Because it doesn't really look like anything we know. I'd like to get rid of the square root. That's what I would like to do. So I make a substitution. I could let x equal the square root of y, or I can write it like this, which is a little bit more convenient. It's the same thing as saying x is the square root of y. And that's my aim, is to replace the square root of y piece. But I write it like this so that the differential is a little easier to handle. If I take differentials on both sides, I get 2x dx equals dy. And I need to also adjust my limits. When y is equal to 0, x is also equal to 0. And when y is equal to r, x will be equal to r squared, square root of r. So that's my substitution. You can write it the other way too. You can write x equals square root y or u equals square root y and take the differentials normally. It's just a little bit harder to make this piece go. But it would work out fine. Just a little sloppier, and I'm trying to show you nice ways to do things. So I have the limit as r goes to infinity, integral 0 to square root of r. dy is now 2x dx, so I'll have 2x e to the negative x dx, like this. So take a second, see if you can follow how we get to this integrand. It's not too bad. If you went the other route, if you wanted to write x equals square root y, then dx would be 1 over 2 square roots of y dy. And you would have to replace the square root of y with x to make it look right, to make it substitutable. I can run through that, but first let's finish this, because from here we're going to need some integration by parts. I'll let u be 2x and dv be e to the negative x, following Lipet. du is then 2 dx, and v is negative e to the negative x. And I get lim r to infinity. And I'll open up some parentheses here because I'm about to replace this whole thing by his IBP equivalent. That's negative 2x e to the negative x evaluated from 0 to the square root of r minus the integral from 0 to the square root of r v du. This negative will make this guy positive. Maybe I'll do it in 2 steps. So I'll write negative e to the negative x times 2 dx. And we'll just do that 1 step per line. So here's my output from IBP. You could have jumped in with IBP right away, but I think it's harder to see that this is an IBP problem without making that substitution first. That's a nice substitution to me. So then a few things. I'll evaluate the piece out front here from bound to bound. I'll pop this negative and this 2 out. When I plug in my upper bound, square root of r, here I'll have negative 2 square roots of r e to the negative r, square root of r. And when I plug in 0, I get 0. I'll have negative 2 times 0 times e to the negative 0. That's negative 2 times 0 times 1, which is 0. And then this piece will be plus 2 times the integral from 0 to square root r e to the negative x dx. Everybody good so far? It's definitely a little sneaky. The sub is a little bit sneaky. And then doing IBP within an improper integral might feel like a lot of work, but if you look at it all at once, it's really not too bad. I'm not going to worry about the limit just yet. I'll go ahead and evaluate my antiderivative, and then we'll worry about the limits. When I find an antiderivative for e to the negative x, that's the same as my dv to v step there. That's e to the negative x. So this will be minus 2 e to the negative x evaluated from 0 to root r. And then after I do that evaluation, then I will take my limit. So my last calculus step here, my last step before I take my limit, looks like this. I'll have here e to the negative square root r minus e to the negative 0. So we're looking like that. E to the negative 0 is e to the 0 is 1. So this piece right here is 1. So I'm going to push the page up. And we'll continue from there. this is equal to the limit as r goes to infinity, negative 2 root r e to the negative root r minus 2 e to the negative root r. Distribute this negative 2 and you get plus 2 like that. So I distribute this guy. E to the negative 0 is 1, so negative 2 times negative 1 is positive 2. Everything else just coming along for the ride. And the question is, well, what do I do with this piece? What do I do with this piece? This piece I think is easier than the other one. As r goes to infinity, so I'll write it out. As r goes to infinity, we know that square root r goes to infinity. So lim r to infinity, negative 2 e to the negative root r, that middle piece, that's the same as lim r to infinity, negative 2 over e to the root r. That's going to be negative 2 over e to the infinity, which is negative 2 over infinity, which is 0. And again, this step, we should not be relying on decimals. These limits are limits we need to know. If you don't remember these, look in your book in section 2.6. It's covered in the first few weeks of Calc 1, limits at infinity. It's good stuff. It's stuff that we must know, and it's very, very important for everything that we're going to be doing in this middle third of the course. Lots and lots of limits at infinity. So that middle piece is going to go to 0. But what about this piece? Here we have a bit of a dilemma. I can pop out the negative 2, and I'm left with limit r to infinity, root r times e to the negative root r is 1 over e to the root r, like we used a minute ago. But now this first piece wants to go to infinity. This second piece wants to go to 0. So I'm going to use these kind of quote bunnies for looks like. This looks like infinity times 0. What is infinity times 0? Good, it's indeterminate. This could go either way. Infinity times 0 is what's called an indeterminate form or an indeterminate product. And the way we handle things like this is usually L'Hopital's rule, but you have to rewrite it as a fraction first. So if you take a really, really big number and you multiply by something really, really close to 0, you could get a really, really big number, or you could get something that's really, really close to 0. In fact, you could get any real number out. So as we move into sequences in 11.1, I'm going to talk a little bit more about indeterminate forms and kind of give you a refresher on that stuff from Calc 1. But this is going to be handled by L'Hopital's rule. So I'll have negative 2 lim r to infinity root r over e to the root r, like so. And you could make a substitution in this limit, or you could attack it directly with L'Hopital's rule. I'm going to attack it directly. Anytime you use L'Hopital's rule, it's important that you let your reader know what you're doing, because L'Hopital's rule looks weird as hell without a little, like, where did this come from? I like to put an L-H or an L''H over top of the equals sign at the step where I'm using L'Hopital's rule. Remember what L'Hopital's rule says? It says, if your limit looks like infinity over infinity, which this one does, The top is going to infinity, the bottom is going to infinity. Then you can differentiate top and bottom and try again. If I differentiate the top, I get 1 over 2 square roots of r. That's the derivative of root r. And if I differentiate the bottom, I get e to the root r times 1 over 2 square roots of r. It's a chain rule derivative. Okay, so that's the derivative of the top and the derivative of the bottom. And these cancel. So I get -2 times the limit as r goes to infinity, 1 over e root r, which is a limit we calculated earlier. This is 0. So let's come back to our problem. We are here, and we just did all this side work to sort out the relevant limits. This piece I knew right away goes to 0. This piece I just discovered with L'Hopital's rule also goes to 0. So my whole thing is equal to 0 minus 0 plus 2. Therefore, the integral from 0 to infinity e to the negative square root y dy converges to 2. Sorry, that's a therefore. Right, this is a good problem. It's not super easy at all, right? You've got a substitution followed by IBP followed by some somewhat tricky limits. That tricky limit required you remembering L'Hopital's rule. So don't stress if this was a challenging problem for you. And if you need more time on homework 6, submit an extension request. I went in this morning, cleared them all out, and I fully expect to see a few more after class. That's okay. Are there any questions about any of the steps here? Or would anybody like to see the previous page for a bit before we move on? Sorry, my wife just had a man come into her store that got in a nasty motorcycle accident. So she's chastising me for wanting a motorcycle. Anybody want to see the previous page or want to talk about any other parts of this problem? Is there anything here that we would like to dive a little deeper into or look at for a little longer? Okay then. So I don't want to spend all of our class time today solving problems from that previous homework. I do know that there were a couple others that you guys wanted to look at, so I'm going to take a peek at the chat here. Is there anything else in there that we desperately want to see? A few people asked for 12 and 13, so we did those. I see 2 people asked for 23. So let's take a quick look at 23, and then we're going to talk about sequences. Ah, yeah, this is a classic. Love this problem. Word of warning, problems of this type have shown up on my exams more than once. So for what values of p does the following integral converge? Good question. I'm going to leave off the 39 there. Here we are. So for what values of p, oh, focus. For what values of p does the integral from e to infinity 1 over x times the pth power of ln x converge? First we write as a limit, always. And then I would make a substitution. This ln of x is kind of weird, and I happen to have a 1 over x hanging out. So if I let z be the natural log of x, then dz will be 1 over x dx, which I have sitting here. Also my bounds, when x is equal to e, z would be equal to the ln of e, which is 1. And when x is equal to r, z will be the ln of r. Okay, so you notice I'm always being very careful with my bounds. Writing this as the ln of r might feel clunky, but it is the thing to do. So we get out the limit as r goes to infinity, integral 1 to ln of r, 1 over z to the p dz. And now here I can do something quite sneaky. As r goes to infinity, the natural log of r goes to infinity. It goes slowly, but it goes to infinity. So I'd say recall lim r to infinity, ln of r equals infinity. So I can rewrite this as an improper integral. I can go what might feel like a backward step, writing this as the integral from 1 to infinity, 1 over z to the p dz. Now, why would I want to do that? We say in order to evaluate these integrals, we have to write them as limits. We can't do any of our good shit with an upper bound of infinity. So why on earth would I want to go back and rewrite this like this? Why would I want to get rid of that limit and rewrite it as an improper integral? Because it's a p integral. Yeah, Morgan nailed it. This is a p integral. The original integral is not a p integral, but this one is. And we know when p integrals converge. That integral will converge if p is greater than 1 and diverge if p is less than or equal to 1. And since this integral, which is a p integral, is equivalent to my original integral, I can say that my original integral will converge. Oh, yeah. If p is bigger than 1 and diverge if p is less than or equal to 1. So it's important you remember your theorems. you don't want to say that the original integral is a p integral because it's not. P integrals are just 1 over your variable to a power. If there's anything else, then it's not a p integral. But this substitution turns our integral into a p integral. And that p integral I can apply my theorem to. Since that integral is equal to the original integral, my original integral must converge or diverge according to the same rules. Yeah, isn't it? I get like the hair on the back of my neck stands up when I see this shit. It makes me so happy. So it's very, very sneaky, right? Very, very sneaky. Mathematicians love these sort of sneaky things. I love these sort of sneaky things. And hence, you might want to be prepared for sneaky things like this on the test. Any questions about this problem? It might. Yeah, it might. Anything that we're wondering about here? Anything feel weird? We can, if we assume that p is larger than 1, then we can come back here. So Fernando asks, can we evaluate the integral? If we know it converges, can we find out what the value is? And yeah. We pick up from lim r to infinity integral 1 to ln r 1 over z to the p dz, assuming p is bigger than 1. So then that would be equal to, since p is bigger than 1, this is going to be a power rule thing. So that's z to the negative p, and he will integrate to z to the negative p plus 1 divided by negative p plus 1. And that needs to be evaluated from 1 to the natural log of r. And then we need a limit out front. Sorry. I can pop out the constant factor from the denominator. That's 1 over 1 minus p, lim r to infinity, ln r raised to the 1 minus pth power minus ln 1 raised to the 1 minus p, right? Negative p plus 1 is the same as 1 minus p. And then as r goes to infinity, here's the thing, since 1 minus p is, how do I say this? Since p is bigger than 1, 1 minus p is negative. So this is 1 over 1 minus p times the limit as r goes to infinity. Really, this term belongs downstairs. Is 1 over ln r raised to the p minus 1. And then what is this? Is this the natural log of 1? So that's 0. So it appears to me that as r goes to infinity, this piece is going to go to 0. Because you'll have 1 over infinity, so you'll have 1 over 1 minus p. Did I make that substitution? Z equals 1. Oh, I'm sorry, this isn't ln of 1, it's just 1. Yeah, there it is. So this isn't 0. This is just 1 to the 1 minus p. So I have 1 over 1 minus p times this piece does go to 0 minus 1, like that. And so you get negative 1 over 1 minus p out. Yeah, sorry, my upper bound is ln r. My bottom bound is not ln of 1, it's just 1. So in the event that this integral converges, how did I pull out the 1 over 1 minus p? It's a constant. So the factor of 1 over 1 minus p, at this step, I go, okay, this is lim r to infinity, bracket 1 over 1 minus p times z to the 1 minus p. That's the kind of in-between step there. And then 1 over 1 minus p is constant because p is constant. So he can pop out the limit. He pops out the evaluation bracket, this piece comes all the way out front, just like any other constant would. And we're evaluating from 1 to the natural log of r. So yeah, in the event that these integrals converge, you get negative 1 over 1 minus p, which is the same as 1 over p minus 1. Good stuff, right? There are similar games that can be played with series and sequences, asking for what values of this parameter or that parameter does this thing converge or diverge. And they make for good problems. They make for problems that are good test questions. Now I want to begin 11.1 in earnest. So this is the second object we've studied for which there is a notion of convergence. These are going to be sequences. In order for them to be interesting, sequences are going to be infinite. I'm not really interested in finite sequences, but the definition of a sequence, and we mentioned this on Friday, is a function whose domain is maybe a subset of the natural numbers. And depending on whether you're French or not, the natural numbers may or may not include 0. I think of them as including 0, so that's like 0, 1, 2, 3. Positive whole numbers or non-negative whole numbers are the natural numbers, or counting numbers. So a function whose domain is whole numbers, that's a sequence. Another way of saying this is a sequence is just an ordered list of numbers. Really, they mean the same thing. If you have an ordered list of objects, then there's a first object, a second object, a third object, and that defines a function. 1 goes to the first object, 2 goes to the second object, 3 goes to the third object. Your book uses the first definition, but I find the second definition useful for intuition. There's also some special notation. Usually, instead of writing like f of x, we write, usually it's an a and with a subscript n. So like instead of f of 1, this would be like analogous to a1. F of 2 would be analogous to a2. F of 3 is analogous to a3, and so on. This is the word def, just for definition. Def 2 says a sequence is an ordered list of numbers. Yeah, a sequence is an ordered, sorry if that's illegible, ordered list of numbers. A little bit other notation stuff. If I want to refer to the nth term of the sequence, all right, just an. The sequence overall, I'll write curly braces AN. And sometimes down here, you'll see the starting value for n, and then an infinity up here to demonstrate that the range or the domain is all natural numbers from 1 to infinity. And then sometimes you'll see something like this. The curly braces with the terms listed inside. So these are the different notations that we use to refer to sequences, at least in this class. I have pretty standard notation. This is the notation your textbook uses. Every undergraduate calculus class uses this notation. We read this as AN, not A to the N. If you want to say A sub N or A of N, those would both be acceptable also. But it's definitely not a power, so we don't want to say A to the N. That's not correct. Some examples of sequences. The sequence defined by the rule AN equals N, or N equals 1, 2, 3, and so on, has first term, I know this might be silly, A1 equals 1. Second term, A2 equals 2, and so on. Third term, A3 equals 3. Right, so this is just it's like the function f of x equals x, same thing, instead. Yeah, STEAD, stead. So instead of writing f of x for the output associated with the input x, we write AN for the output of the sequence associated with the input n. So the sequence here, AN equals n, is like the function f of x equals x. Its output is whatever its input is. The only difference is here, rather than looking at all possible inputs running over the real numbers, I look only at all possible inputs running over the natural numbers. And so we can talk about the graph of the sequence AN equals n. A1 is equal to 1. So the point 1, 1 is on the graph. A2 is equal to 2. So the point 2, 2 is on the graph. A3 equals 3. So 3, 3 is on the graph. A4 equals 4. So 4, 4 is on the graph. And what you notice is that these dots, which is the graph of the sequence, live along the graph y equals x. Yeah, I should really. In your notes, draw these in as dotted lines, please. So notice that the graph of the sequence, which is just the dots, lives along the graph of f of x equals x. This relationship between functions of a continuous variable x and sequences that the dots are trapped along that curve or along whatever that graph shape is will be useful to us as we start to develop theorems about sequences. We will from time to time relate a sequence back to a continuous function, but not always. So sometimes it's useful to do that. And I just want to point out that this is what the graph of a sequence looks like. It's just the dots. And that sometimes those dots live along some nice smooth function, and we can learn from that smooth function about the dots. And moving along, I'd like to look at another example of a sequence. Simon mentioned one in chat called the Fibonacci sequence. We'll talk about that in a second, but I want to look at one other first. There's a famous sequence called the harmonic sequence. If you're interested at all in music theory, then you've probably heard about this. The way the Pythagoreans, who are also really into music, not just into triangles, started studying music was by, if you took pre-calc with me, we talked about these also. It's by looking at integer divisions of the string. So if you cut a string in half and you pluck it, you'll get a tone that sounds nice when played over the tone from the original string. So that's called the first harmonic. And if you continue looking at integer divisions, you get other harmonics. So the harmonic sequence is the one defined by the rule an equals 1 over n. Its first term, a1, is 1 over 1, which is 1. a2 is 1/2. a3 is 1/3. a4 is 1/4. And you can keep going and write down as many terms as you want. Its graph I'm going to mark this up here as 1 on the y-axis, and then 1, 2, 3, 4, and so on. So this is my n-axis, and this is the graph y equals an, or y equals 1 over n. a1 is 1. So the point 1, 1 is on the graph. I'll mark this as 1/2. a2 is 1/2. If that's 1/2, then 1/3 is like right here. a3 is 1/3. And if that's 1/3, then 1/4 is like right here. a4 is 1/4, and so on. All right, so that's the graph of the harmonic sequence. a5 would be 1/5, which would be like right here. And so you get this pattern here, right? We're like diving down on towards the x-axis, and we're going to get closer and closer to the x-axis or n-axis as we go out further and further. Just like the previous sequence was, his graph is trapped along the graph f of x equals x. This guy's dots are trapped along the graph f of x equals 1 over x. And stuff we know about 1 over x will help us understand this sequence better when we talk about limits. But for now, I just want you to get comfy with the idea that the graph of a sequence is just a collection of dots. A sequence is an ordered list of numbers, or equivalently, a function whose domain is the natural numbers or some subset thereof. Another sequence that we have studied is the factorial sequence. We talked a little bit about that a while ago. But before we talk about him, let me look at something a little bit different. Okay. Yeah, let's look at 2 other sequences as examples here. And here I'm going to use this other notation just to get us practice. So let's graph the sequence -1 to the n, where n is allowed to run from 0 to infinity. Focus, you should. This is what's known as an alternating sequence because its signs bounce back and forth. A0, here I start at the input 0 because it tells me to do so, is -1 to the 0. That's 1. A1 is -1 to the 1. That's -1. A2 is -1 squared. That's +1 again. A3 is -1 cubed. That's -1. A4 is -1 to the 4. That's +1 again. So if I wanted to graph this guy, I'll mark this as 1. I'll mark this as -1. And then here's 1, 2, 3, 4, and so on. A0 is up here. A0 is 1. A1 is down here, is -1. A2 is back up here, it's +1. A3 is back down here, it's -1. A4 is up here. A5, we didn't calculate it, but A5 would be down here. A6 would be up here, and so on. So this guy does not come from, or cannot be thought of easily as points along the graph of some continuous valued function, continuous variable function. If you swap in an x for the n there, you do not get something nice. The function -1 to the x is far from continuous. So this is the first sequence we've seen where it's not the restriction of some well-understood continuous function to the natural numbers. We're not just looking at dots along some smooth graph that we know. But it is nevertheless a sequence. All right. Let's look at the Fibonacci sequence next. These belong to a family of sequences called recursive sequences. So a recursive sequence, or a sequence, is called recursive R-E-C-U-R-S-I-V-E. It's called recursive if, rather than coming from an explicit formula, for the nth term, it's given by an initial condition together with a rule for calculating the next term as a combination of previous terms. All right, this is what it means for a sequence to be recursive. So rather than telling you, okay, to get the fifth term, just like -1 to the 5 or 1/5. Here, I would say to get the fifth term, do some shit involving terms 1 through 4. The classic example is called the Fibonacci sequence. So here, I'll use A's again, why not? A0 is defined to be 1, And the rule, A1 is also defined to be 1. And then the rule is that AN plus 2 is equal to AN plus 1 plus AN. So in order to get the next guy, you add up the previous two. A0, I'm given. These are called the initial conditions. And this is my recursion rule. So if I wanted to know what A2 is, according to this recursion rule, it should be A1 plus A0. And A1 and A0 were given to me. So this is 1 plus 1, which is 2. If I want to find A3, according to this recursion rule, that should be A2 plus A1, the sum of the two previous guys. A2 is 2, A1 is 1, so that's 2 plus 1 is 3. If I want to find A4, that should be A3 plus A2, which is 3 plus 2, which is 5. So the Fibonacci sequence goes 1, 1, 2, 3, 5. The next term, A5, should be A4 plus A3 is 5 plus 3, which is 8. And the next term would be 5 plus 8, which is 13, and so on. Yeah, so this is called the Fibonacci sequence. And it's got a lot of neat mathematical properties, but for us, it's just an example of a recursive sequence. So these are sequences. You're going to be getting to know them pretty well. I want to introduce you to the main operation that we're going to be doing with sequences, and then we'll call it a day there. Since these functions only take in natural numbers, whole numbers, I can't really talk about derivatives because there is no like curve. So I can't really talk about like slope. And since there's no curve, I really also can't talk about areas underneath them, at least not in any obvious way. So what the hell kind of calculus are we going to do with these? The main calculus operation we perform on sequences is lim n to infinity. In other words, I want to know if the terms of the sequence are getting closer and closer and closer to any particular number. So here's the definition of convergence for a sequence. We say the sequence AN converges if lim n to infinity AN exists and is finite. Otherwise, we say the sequence diverges. All right, so limits at infinity are the main game here. This is your second notion of convergence. You're going to have two more before the class is over. We have convergence of improper integrals, convergence of sequences. After this, we'll talk about convergence of series and then convergence of power series. So I would make sure you keep this shit straight in your head. An integral converging has its own definition. A sequence converging has its own definition, and later series will have their own definition. But we use the same words, converge and diverge. So make sure you're comfy with this idea. I will show you a quick example, and then we're going to sign out for the day. The harmonic sequence. An equals 1 over n has limit lim n to infinity an is lim n to infinity 1 over n is 1 over infinity, which is 0. So we say that an equals 1 over n is a convergent sequence. With limit 0. The other sequences we've looked at today, they're divergent. An equals n, that just gets big. The Fibonacci sequence actually gets big faster. Fibonacci sequence is a rapidly divergent sequence. All of the rules you had for limits at infinity in Calc 1, in section 2.6 in the textbook, are going to come back here in a big way. So you want to go back and study those maybe. I will develop for you a handful of theorems on sequences, helping us figure out when they converge and when they diverge. But none of it is going to make sense unless you're comfy with limits at infinity from the Calc 1 perspective. So please take the time to remind yourself the important limits there. Do I have it open yet? Yeah, I do here. So come back here to section 2.6 and make sure you're comfy with all this shit. And then read section 11.1. Because there's a bunch of theorems here. So I implored you last week to read this. I'll implore you again today. Oh, why did my screen share stop? So I strongly encourage you to read section 11.1 in the textbook. If you haven't done, now is the moment. Finish up homework 6. They talk about the Fibonacci sequence. They talk about some other examples that we haven't talked about. On Wednesday, we are going to talk about geometric sequences, and then we'll start developing those theorems. I'll also remind you some tricks for calculating these limits. There is a way to make this very rigorous involving epsilons. That is, if you're into that sort of stuff, if you like the real analysis stuff, I like it, but I'm not allowed to force you to do it. The basic idea is that if you can get as close as you want to L and stay as close as you want to L by taking n large enough, then that limit exists and that sequence converges. And there's some really nice pictures in here, but it's the theorems that I would pay extra special attention to if I was coming back here and looking at this stuff with fresh eyes. So that's what we're gonna go over on Wednesday. Friday, there is unfortunately no class because the 4th of July is Saturday, so we decided to take Friday off. I don't know. That's how it goes. But we're gonna talk about these theorems on Wednesday. There will be a new homework opening up today, and we'll move forward from there. This factorial object that we introduced last time is going to be important all throughout chapter 11. And then we'll have a bunch of theorems on geometric sequences and monotone sequences, stuff like that. So that's where we are. Any questions for me before I sign out here? Sorry. I will, yeah, I'm gonna have an office hour after class here. I need to run downstairs, grab some coffee, and then I'll come back up and start my office hour. Alrighty, so I'm gonna go ahead and sign out. If you guys wanna come by the office hour, I'll see you there. Remember to work hard on getting that homework done. Oh, Nicholas, yeah. Yeah, if you're going to the rocket launch, I would love to see some photos or video of that. That would be awesome. And yeah, that's it. Okay, so I'll see you guys in office hours or on Wednesday.